Yesterday we talked about two variable systems of inequalities, and today we're going to talk about two variable systems of equalities. And as I stated yesterday, our solution within the inequalities was a region of points that satisfied all the inequalities in the given problem. What we're going to look for now are solution points that solve both equations. So what I have for you is I have two equations, y equals 3/4 x plus 3 and y equals 3x minus 6. And I want to know, is that point 4, 6 going to be a solution for both equations? Well, this is as simple as plugging and chugging the point x and y, 4 for x, 6 for y, into both equations and see if both hold true. So in the first equation, I have 6 should equal 3/4 times 4 plus 3. This gives me 6 equals 4 and the 4 reduce, 3 plus 3, 6 equals 6, so that checks. Now, we do the same for the next problem. We have 6 equals 3 times the x value of 4 minus 6. We end up with 12 minus 6, or 6 equals 6. Since that point checks for both equations, it solves the system and is a solution. So the answer is yes. Now, we're going to talk about three different types of systems. One is what we call a dependent and consistent solution, right? Which means basically if I'm given two equations and I try to solve those two equations, I end up with an answer that yields an equality or a true statement, like 0 equals 0. It could be 3 equals 3, 5 equals 5, whatever. We say that system has an infinite number of solutions, and basically if we were to take and graph these two as a line, they would be the same line and graphed on top of each other. So where do they overlap? Everywhere. Now, if we talk about independent and consistent, that means when we solve the system of equations, we end up with a unique point, x and y. And once we get that unique solution, that's where the two lines intersect. This can be seen in this graphic over on the right. If we have an inconsistent solution, that means when we try to solve our system of equalities, we end up with a statement that's not true, like 0 equals 42 in this case. That means there are no solutions, or we have a situation where we have two parallel lines and there's no intersection. So we're going to go through and solve some of these using a variety of techniques and then find our solutions. So in this first case, we have 4x minus 3y is equal to negative 15 and x plus 2y is equal to negative 1. And the first way we're going to solve this is using what we call substitution. Substitution is a process by which we try to isolate a variable and find out what it equals. The easiest variable to isolate in this case is x. X, we know, is equal to negative 2y minus 1. So basically, everywhere I see an x, I can substitute in negative 2y minus 1. Well, I see an x in my upper equation right here. So I'm going to rewrite that. I'm going to say 4 times, instead of x now, I'm going to say negative 2y minus 1. I'll subtract that from 3y and set that equal to negative 15. And then I'm going to go about solving that. So that's negative 8y minus 4 minus 3y is equal to negative 15. So gathering like terms, I have negative 11y equals, and I'm going to bring this -4 over to the other side by adding 4 to both sides, -11. So thus y equals +1. If y is equal to +1, then I can plug that into this equation over here and find out what x is. X is equal to -2 times 1 minus 1, which is -3. Thus, I have a solution point of -3 and 1. And if we wanted to check that to see if both those were solutions, I'd plug them into those two equations. Let's just do it real quick, then we won't do it again. So I have 4 times -3 minus 3 times 1. That's going to be -12 minus 3, which is -15, and that's what it was supposed to be equal to. So that checks. And then the second equation we actually use to solve the point, so we won't even plug it into there because we know it works. All right. One example using substitution. This next equation sets itself up for substitution again because we already have a variable isolated. So we're going to go ahead and use that just one more time for practice. So we have x equaling 14 minus 3y. Substitute the x value into the other equation for x, and I have 3 times 14 minus 3y minus 2y, having pen issues, sorry, is equal to -2. So now I have 52, I lied, 42 minus 9y minus 2y equals -2. This is not looking pretty. So I have now -11y. That's actually not bad. It's -44. So y is equal to 4. Substituting back in, x then will equal 14 minus 3 times 4, or 14 minus 12, which is 2, thus giving me a solution point of 2, 4. Next example. Now, in this case, we have a system set up where I have 4x minus 5y is equal to 6, and 4x plus 6y is equal to 4. Now, most of you know how to do this problem already, but the question is, do you know why it works? Now, when we have an equation, for instance, 3 equals 3, properties of algebra state that we can add the same thing to both sides and get an equality. So I could add 5 to this side, 5 to this side, and I get 8 equals 8, so I get another true statement. Now, the way you've all gone about solving this problem in the past is your Algebra 1 teacher probably said, or even your Algebra 2 teacher said, add these two up and the x's go away, it all works out. And you've all done that, but never asked, why does that work? Well, if we think about this, if I add 6 plus 4, not a problem. We know that's equal to 10. And then when I add these two equations, the 4x's go away and I get y is equal to 10, and that was always good enough for you. But why is that y equals 10 a solution? Well, we know that adding 6 to 4 is 10 once again. But we also know that 4 is equal to this whole quantity over here of -4x plus 6y. So really what I'm doing is I'm adding 4 to both sides of the above equation. So add 4 here, add 4 here, thus the equation stays balanced. That's why that's always worked. So now if I want to find my x value, I just take my 4x minus 5 times my y value, or 10. Set that equal to 6. 56 is going to equal 4x. And x equals 14. So I have 14 and 10 as a solution. This whole process is called elimination. In other words, we're eliminating a variable to solve the system. So now in this case, I don't have anything matching up, which is unfortunate. But what I can do, again, because of the properties of algebra, is I can add whatever I want to either side and not change the problem, just change its look, but not change its actual values or qualities. I can multiply to either side. I can do whatever I want to either side of the equation. If I look at this bottom equation and I want to use elimination, that means I want to get variables to match up. Well, 2 doesn't go into 5, but I know 3 goes into 6. And it would be nice if I could have opposites so that they could just add away. So in order to make opposites, I'm going to multiply both sides of this equation by -2. I have 5x minus 6y is 9. And then I'm going to multiply by -2, giving me -4x plus 6y is equal to -6. And in the previous example, we used elimination. If I add 9 to -6, I get 3. And really, this -4x plus 6y also is equivalent to -6. So I'm adding -6 to both sides of the above equation. In doing that, the 6y is reduced, and I get x equals 3. So I've eliminated a variable to find a new variable. Once I have that x value of 3, I substitute back in. I get 5 times 3 minus 6y equal to 9. Bring the 15 over. I get -6. Equals -6y. Y ends up equaling 1. Substitute back in. 5x minus 6 times 1 is 9. You get 15 equaling 5x, and x equals 3. Thus, solution to the system, 3-1. Couple more. Now, in this system, I look and nothing matches up, so I can't eliminate right away. I notice that 4 doesn't go into 5 evenly, and I notice that 2 doesn't go into 5 evenly. So what I'm going to have to do in this case is probably multiply both equations by something in order to get a variable to be opposite. So I look, and the easiest one that I see is multiplying the top equation by a 5 and the bottom equation by a -2. That's what I see. Okay, you may have saw multiplying the top equation by a 4 and the bottom equation by a -5. Either way, it's going to work out. So I multiply that top equation by 5, I get 25x minus 10y is equal to 5. Bottom equation by -2, I get -8x minus, oops, I'm going to multiply that by a +2, sorry. So I get positive 8x plus 10y. That way I have opposites. And that's going to equal 16. And we're going to add those up. I get 21. is equal to, this is not pretty, 33x. So x equals, 3 goes into both of these, 7 over 11. So now if I want to go back and find the y value, again, I'm going to substitute back in. It's not quite as pretty this time, but we'll do it. We have 4 times 7 over 11. I'm using the bottom equation because it appears to be a little bit smaller. Plus 5y is equal to 8. With 28 over 11 plus 5y equals 8. I can take now 5y and find out what 8 minus 28 over 11 is. Use my calculator. If I want, I end up with 60 over 11. And then I have to take and solve that. So I divide both sides by 5, or I could multiply by a fifth, which is probably easier, at least for me. So I get y equals 60 and the 5 go to a 12, so that's 12 over 11. And thus I have two solutions. Actually I have one solution of x and y. 7 over 11 for my x, 12 over 11 for my y, and I'm out. Now the last problem is a little bit trickier because we have fractions all over the place. And once again, we want to create opposites if at all possible. And the best, I'm not a big fan of fractions. I can work with them, but I prefer not to if I don't have to. So in this case, what I'm going to do is, the first step I'm going to use to get rid of my fractions, or clear the denominator. So I know if I multiply by 6 to both equations, then my denominators will all reduce. So this gets me to 2x minus 3y equals 48. And my second equation will get me to 3x plus 2y is equal to 6. So now what I want to do is I want to create opposites. And I look right away and I see, well, hey, if I multiply my top equation by 2 and my bottom equation by 3, my y's will become opposite. So now I have 4x minus 6y is equal to 96. My bottom equation goes to 9x plus 6y equals 18. I can now eliminate. I have 13x is equal to, what is that, 114. 14. Divide both sides by 13, and unfortunately, it doesn't reduce so nice. Whoops. So I get x equals 114 over 13, which leaves me to find y. Now, if I want to find y, what I'm going to do is probably pick the smallest equation that I have to use. I'm going to go with this 3x plus 2y is equal to 6, because that's pretty small. So I'll say 3 times 114 over 13 plus 2y equals 6. And then we'll have to use some calculator intuition to get this thing done. So 3 times 114 over 13 is 342 over 13 plus 2y is equal to 6. I subtract 132 over 13 from 6, once again using a calculator. And I end up with negative 264 over 13. Divide that guy through. Y equals negative 123 over 13. So my x value, once again, is 114 over 13. My y value is negative 123 over 13. That's about as bad as it's going to get for two variable systems. So next, you got a couple of questions to answer. Fill out the form, and we'll get back to you tomorrow. Bye.